Hi, I'm Dennis. This is George and Andrew, and we're going to present a talk about bypassing crypto and banking applications. Part of our talk is heavily relies on a novel by Anthony Burgess, which is Clockwork Orange, and it is really inspired by that. So the story becomes when we stuck upon a remote banking system. So that was me, Dennis, and my two droogs, and we were sat in the lab making our rassoodocks. Yes, like what to do with the big bank's remote banking system. The bank was one of big European banks, and it was Russian branch of that bank. And this banking system was protected by, hardened by certified crypto, certified by Russian local officials, which is Federal Security Bureau. So what did we see? A remote banking system which deeply into the both sides, client side and server side, heavily relies on crypto. It uses crypto for non-repudiation, so it signs all the requests from the user. For authenticity, so it authenticates users using the crypto, and the protocol between client and server is also encrypted and uses all those crypto stuff. And this banking system complied with regulations of Russian Central Bank. So this was basically the motivation for the bank to use Russian crypto. And it seemed really unbreakable. So at first we saw that, well, the web interface has very simple bugs like XSS and so on, but it seems that we cannot actually exploit them because of crypto. And finally, we broke this crypto. This is the outcome of the whole story. So, what we had at the end, we bypassed non-repudiation. So which means that if we're contesting a remote banking system, what is our main target, main goal? To act from any existing user of this remote banking system and make valid requests, presumably payment requests, for example, as if we are these users. So, bypass second authentication layer, which was powered by enforced with crypto, and this finally allowed us to log into the remote banking system using credentials of any existing user and file valid requests by bypassing the crypto. But we didn't break the crypto actually. It was not like we found a bug in GOST crypto algorithm. This is not the case. We just found a way to go around. I would like to tell a little bit about what kind of systems we're looking at. And basically in this talk we are presenting not only the case study or result of analyzing the specific banking crypto, but rather methodology for pentesting, for finding flows, application-specific or integration-specific flows between in the remote banking systems, which somehow use crypto. And this methodology doesn't rely actually on the fact that this specific remote banking system was using the GOST crypto. It may have used any. We aim at pentesting financial organizations. What do they actually want to do when they're building their remote banking system? They want to ensure that transport is secured between the client and server side, so no one can read the channel, no one can post his request into the channel so that it is from the legitimate user. It should ensure non-repudiation and authenticate users well, encryption is a standard way to solve these tasks. Also, when, at least in Russia, when some bank wants to provide services to organizations, maybe even for individuals, but we're dealing with banking system for organizations, they should comply with local regulations, which imply the central bank recommendations on how they should build their banking systems. And somewhere in the middle of these regulations, they say that you should use government-allowed crypto. And also, often, banks want to protect legacy systems. So maybe a system which started development in the 60s or 70s or maybe 80s, and they want to use this existing application and rework it to comply with local regulations. So they are trying to somehow integrate new crypto with existing systems. And what options, what are the requirements which they have when they start to solve this test? They have a bunch of technical best practices. How to ensure confidentiality, authenticity, non-repudiation, using any kind of crypto, actually, any kind of application levels protocols. They have requirements of compliance, which is using certified crypto, and they have business needs, which may be any, actually. They can use in-house development of this remote banking system. They could outsource it to someone, and they have to choose between these two options, which may lead to some different results in each case. They may choose from between building the remote banking system from scratch or using the legacy systems and somehow integrating it with other stuff like crypto. Well, it's not very common that the bank develops its own remote banking system from scratch. So they somehow balance between in-house development and outsourcing. And as it comes at the end, the full outsourcing, the application development, I mean the remote banking system development, to the company which, for example, develops the certified crypto is not a good option. And here we have, as a case study, the outcome of such integration. So, the solution may be like this for the bank. They take crypto-hardened thick client, which may be a thick application or web browser plus client-side proxy, and the server-side application-specific crypto proxy. And they build the logic upon HTTP. This means that they have usually general purpose web browser on one side, on the client side, and an Air-based application system on the server side. And between them, they build a cryptographic subsystem, which often is a black box for the client and a web application server side. We have a client, we have a crypto tunnel, we have 2 points of tunnel endpoints. client side and server side, and the application server. The tunnel endpoint on the client side checks, it assigns requests, it makes basic authentication, and it may put some application-specific information into custom HTTP headers. And the crypto server in the middle between the application server and the client verifies the signatures, verifies the crypto part of the protocol, and then passes checked requests to the application server. I should focus on the fact that when the request passes the crypto server to the application, usually application developer thinks that the request he received from the crypto server is cryptographically checked and valid, and he should not check it once more. And I pass to the Andrew. Yeah.
Hello. I'm going to talk about methodology, that is how to think when we're dealing with such systems. And one important fact that I'd like to point out is that we should think of this architecture basically as a black box crypto that is between server side and endpoint application server and the client, and that application server looks at this crypto as an HTTP client. Basically, crypto server, after his checks for validity and so on, issues a request, passes upstream to application server, and acts as client. So the important fact that the trust boundary between them is stripped of cryptography. So server side has to trust, as Dennis said, every header and every parameter that crypto server issues upstream. So as a guy from some kind of academia, I like to talk about methodology, about general ways, and after I finish, I will pass word to George, who will make a case study how this methodology really worked in this our case. But I'd like to point out that this is a general, this should be like a general kind of thinking. Well, when we start analyzing this kind of architecture, like common sense suggests us that there are certain kinds of well-known issues that spring out and are publicly available in internet, like in common vulnerability enumeration as instances and so on. So 3 points that come into mind are that there are errors in handling with crypto, like crypto could be GOST certified and like everything, but the usage of it would be incorrect. Like the second thing is that one doesn't simply implement an HTTP client, a server, or parser, his own parser. I don't know, but everybody wants to implement their own XML, HTTP parser. It's weird. And of course, there are some kind of errors. And general thinking just suggests that if we have several parsers in a row that handle the same HTTP request, they would handle it with inconsistencies. So if we fingerprint those inconsistencies, we could build some kind of weird smuggled requests that would be treated unequally on a middle end and on a back end. So the basic objective is to find those differences in handling and to exploit them. just to pass, for example, signature validation and to exploit the trust relationship between crypto server and application server. So the three steps I'm going to talk about are the reversing client-side features. That is not rocket science because we have everything on client. And then the second part is fingerprinting server-side features and the integration protocol itself. So basically, three parts in this architecture should be fingerprinted in order to find inconsistencies. That's pretty logical. So let's start with client side and with crypto. So basically, we have possibility to analyze process, analyze traffic on the client side. We have possibility to launch our favorite debugger to know everything that we want. So the basic questions in this survey would be fingerprinting of HTTP client that is used to submit requests into tunnel. So, for example, if we talk about client-side proxy server that receives requests from browser and transmits them over secure transport, so that would be an HTTP client implemented somehow. Then we would like to fingerprint what kind of methods, HTTP methods are allowed, and what kind of information is cryptographically signed, like the whole request, query string, headers, post body, etc. And at the same point, we'd like to know what additional information, metadata, is attached to the initial requests as it is passed onto crypto tunnel. So it could be like additional headers with key ID identification. So because somehow client side should communicate user identity that is by means of crypto, by means of the crypto that is used. So as a backup reasoning for this step, there are certain kinds of bugs that are perfectly known, and this list springs all over again, and in each point suggests that somehow crypto wasn't properly used. The second step would be fingerprinting of HTTP parsers. Well, there are known techniques to do that. That is HTTP parameter pollution, HTTP parameter HPC, okay, because I don't know how to tell that word, contamination. We'd like to know how duplicate headers are treated, because, for example, if we submit several content length headers that have unequal values, which header would be processed by applications by crypto server, and which one would be processed and by the backend server. So basically, this work yields us a list of peculiarities of HTTP parsers on crypto server side and on an application server side. Well, then we're going to fingerprint web servers themselves, also on crypto server side and application server side. That is, we'd like to know what methods they support, what protocol versions they do support, whether they know how to treat chunk encoding or multi-part requests, etc. Whether they are able to streamline HTTP requests into one HTTP connection, etc. So, because nothing ever changes. Okay, well known that HTTP parameter pollution is used to bypass every kind of IPS web application firewall that is on the way to application server. So these inconsistencies spring up and down. So the crucial part of our fingerprinting is the fingerprinting of integration protocol itself. Because a crypto server, again, should somehow communicate the validity or invalidity of the requests received from the user to the backend. And that should usually be some kind of additional headers. We can remember the same kind of communication in mobile networks. I don't know if anyone remember this technique published in Top 10 Hacking Techniques by Jeremy Grossman, that mobile networks put additional header that is trusted by application servers in that mobile network, and so spoofing this header would yield us the possibility to act as any mobile user in that network. So you can Google it. So, okay, how do we know what kind of headers are used to communicate the identity, for example, of the user that was verified by crypto server? So, in fact, it could be just those headers that were put on the client side into that were added on the client side to requests as they pass to a cryptographical tunnel, and they could be different. If they are different, so we have basically several methods to know them that are trace requests, but that would not work in most cases. The other ways are to find a debug interface in a web application that prints out requests that were received, that are also one could possibly read documentation if this solution, crypto solution, is well known and is a product. Well, you can always social engineer with developers of such solution, acting as a user of such tunnel and pretending you cannot configure and write your own application server. So the fact that at this point we should know the list of peculiarities and headers that carry out the identity of the user from crypto server to application server. And now I'd like to pass mic to George, who is going to present how this methodology worked out in our case.
Thanks, Andrew. Okay, we're done with the boring part, with the science. Let's rock. Okay, well, it all started as an ordinary penetration testing. You know, they said, here is our shiny remote banking system, which is a normal web application, which can be accessed through some kind of cryptographical black box with the certified crypto providers inside. They said, well, of course, we instantly found some client-side and server-side bugs, logic vulnerabilities, injections, etc. One of our findings was a bug which allowed to change password for any user. So basically, that's a game over. Yeah? Yes, but not exactly. When we gave the report to the developers, they said, well, we have the shiny crypto inside. So first of all your requests are cryptographically signed. So when you are trying to attack and when you do the attacks, your crypto-signed vectors will be a great hard evidence against you in the court, because they are cryptographically signed with your key, and the key was passed to you in an agreement which you signed by hand, etc., etc., etc. Also, the cryptographical channel somehow ensures authenticity. For example, if you hijack the session of another user and try to use the session ID in your cryptographical channel, it won't let you do that. So they said, well, that's not so critical, not so severe, guys. Okay, so we have no choice but to start reverse engineering the client. The client was a closed source, of course, Windows application, a Windows binary. The first thing to try is actually to watch the traffic and try to find out if the traffic dump maybe gives us some clues, but no, there was completely binary rubbish, no clues. No documentation, the protocol is custom, no online docs, etc., etc. And as it is a penetration testing exercise, we didn't have actually lots of time to, read through the assembly, do long debugging sessions. So that seemed rather tough. Well, what we immediately noticed is the fact that the client itself, the binary, uses the crypto primitives which are implemented in the shared libraries which are bundled with the client. So, of course, the lazy way to fingerprint the protocol and discover the inner workings of the client side of the tunnel is to hook the library calls and make API call traces which contain calls to the cryptographical API and to common APIs such as Windows sockets to correlate them and to find out which data is encrypted and which encrypted portions go to the as an arguments to, for example, send system call, API call, etc. Of course, these traces should be filtered in order to get meaningful data, which is not 25,000 API calls, which is unprocessable by eyes. And there is a tool for this, which is quite widespread, called API Monitor, which does exactly this. So this is the example library called Trace, which has the crypto-specific calls as well as the networking calls. So what we can see here, this is the call to encrypt the data, which is about to be transmitted through the crypto tunnel. And the API monitor lets us to actually see the parameters to the API calls. So what we immediately see is the following. Our request before being sent through the tunnel was modified. There were several new headers that were added to our request before the encryption and sending out to the tunnel. So the certificate number is basically the ID of the key. Each user has his own key with his own ID. The form data is actually the part of the request which is signed, and we will verify that in a moment. What we see here is that the URL is not signed, but the query string is. And the signature is stored in the separate header. Okay, so if we scroll up a little bit of this trace, we can actually find that indeed this query string was the argument to the signature, to the signing function. Okay, then the data is sent through the tunnel, we receive the encrypted response, decrypt it, and then we send the decrypted response back to the browser of the user, because you remember that this is a client-side proxy, so it receives request from the user, does magical stuff with it, and sends the result back to the user, acts as a HTTP proxy. Okay, so when our browser sends HTTP request like this, the tunnel the request which is sent through tunnel is modified like this. Okay, some further notices from the reversing of the client side. We saw that the proxy assigns query string for GET requests and message body for POST requests. Of course we checked, because the API monitor gives us the ability to make breakpoints in the API traces and modify the parameters, so we can actually smuggle this data. And we saw that, yeah, the server actually checks that the form data header actually reflects the query or the post body. That the server actually checks that the certificate number is the number of the key used to, during the handshake when the crypto tunnel was built. And after that, the web application checks that the certificate number, which is passed to it in a header, actually matches the user ID of current user. If it is a session already established, it just compares user ID from the session, and if you try to log in, it won't let you log in if the certificate number is invalid. Well, no clues here, but of course, when we apply our methods and test the HTTP parser implementations for inconsistencies, we immediately found some curious and amusing bugs. First of all, what happens if you try to issue a head request? A head request is different from the GET request in that the response does not contain a header, and apart from this, nothing else is different. So, we found that the cryptographical proxy didn't think that you could do some meaningful actions with the head requests. So no signature, no cryptographical signing, no signature validation at the other end of the tunnel, etc., etc., etc. So the second, of course, point is to look for HTTP parameter pollution and see what happens if we have two parameters with the same name but different values in the query string for the post request and in the body. Well, it appears, it happens so that the tunnel signs and verifies signature only for the body part of the request, not for the query string. And the web application itself uses the value from the query string, but not the value from the body. So immediately, this request has a cryptographical signature of the parameters which are completely benign. No attacks, no anything. And the web application actually processes the first one, which is not signed. So these are the two methods that we're able to bypass non-repudiation. Because using head requests, we're able to do stuff without generating any signatures which will cryptographically identify us. And using post requests, we were able to pretend that the data is benign, because the cryptographical tunnel, of course, logs the form data and the signature in order to use that later. Okay, well, of course, you may ask, so what? Who even cares about, cryptographically signed evidence if you can just knock at your door and say, well. So we also needed to bypass authentication. Well, as I said previously, we discovered a bug which is not related to crypto at all, which allowed us to change password for any user. But we could not actually log in as that user because, well, this message in Russian says that your certificate number is invalid. You shall not pass. Yeah, but there is a cool feature in HTTP 1.1 called TCP connection streamlining, which allows us to stick together 2 or 3 or whatever you want, whatever number you want of HTTP requests and send them into one TCP session. So what we discovered was if you have a head request with a body and you append any other request to the end, the crypto proxy actually thinks that it's one request, one head request with body, and it thinks that the body of the request goes all the way to the end of the TCP, to the TCP transmission. So the bug here is actually not checking for content length, which of course, this is the result of adding the crypto metadata to our crafted request. And as you can see, we are free to put these control headers and put any values in them. I forgot to mention that if you try to put a certificate number header in the first request, it will be removed by the proxy and substituted with the right one. So that's basically the way to bypass authentication. And this is how we were able to log in as any user, to issue transactions, to look at account details, etc. And I think we think that this case study perfectly showcases that when you try to integrate, the cryptographically hard to break solution, which is known to be secure, you have to be very careful about your implementation, about the integration details, and about protocol, application level protocol parsing. So now a quick demo for you. We apologize that we had to anonymize it, usually because, of course, of the non-disclosure agreement. So what you see here is the user starts a crypto proxy, specifies which of his identities he wants to use. And now he's able, through this proxy, to log in to the application. This is the normal login. You just enter the username, the password, press the button, wait for a little bit, and now you have the user interface of the remote banking system, which says that your username is ADM350 and you're authorized. Okay, now let's try to use this browser to submit valid credentials for other user. And immediately we see that even with valid credentials, we cannot log in. The proxy provides some convenient logs in which we can find the important details. Now, using the vulnerabilities that we found, we developed our own proxy, which uses the crypto proxy. So see what happens when we use our malicious proxy to bypass the crypto authentication. So we just enter the details once again, and we are logged in as the user 360, for which we don't have crypto keys. And we're able to do everything you want in this web interface. Okay, the important thing to mention here, oh yeah, it is visible. So from the viewpoint of the proxy, of the each side of the proxy, the requests are head requests to some, we chose to use head request for the login function itself because it takes lots of time for the application to process your credentials initially, and it gives us lots of time to for the application to process second request in parallel and give us the results, because we experience some truncation of the second response when the first request was a short one. So that's it for the demo. And I think we can finish up. The word goes to Dennis again.
Okay. So I want to summarize a little bit what we have found. We found bugs into integration part of the crypto and existing or maybe customly developed banking application, and bugs were in how developers of the crypto proxy how they actually know the internet part of the stack, how much they know about HTTP. They didn't actually care about that actions may be taken by head requests, or they didn't care that multiple HTTP requests may go one after another in single TCP connection. And despite of the fact that banking application as a whole was tightly integrated with the crypto, and they used really heavy full-weight crypto in order to sign individual parts of user requests. This difference between how developers see the protocol part of their application and how they see the crypto part, this difference leads to what we see here. So finally, we may act as if there is no crypto at all. We may log in as any existing value user, just changing his password beforehand and then bypassing the crypto. And then from the user interface, we may file payment documents or something which may be then processed by the system as if the user was actually authenticated with his private key. And I would like to say what lessons did we learn for ourselves, and maybe this will be valuable for others. This is how actually we saw this crypto at the beginning. So it's very uncommon for the pen tester to try to break the cryptographic protocols and so on. They try to find simpler ways. So, but then when we see that we can just do nothing, very simple bugs which can be exploited, and some kind of curiosity rises, and we try to look closer at this crypto part, and maybe there are things which could be interesting even for non-crypto guys. And yes, this leads us to the thing that Adi Shamir mentioned on the recent RSA conference 2013, that modern systems which use cryptography are usually exploited as if like there is no cryptography at all. There are always some bugs which allow a curious analyzer, a curious pen tester, or an attacker to find ways to bypass this cryptography. And we have successful bypass and happy pentesters at the results. That's all about the talk. I have time to speak a little about ourselves. We represent different entities. Moscow State University, it's myself. We have information security lab there. Solid Lab is a pen testing company, and we have a team of students which also participate in pen tests, which is Bushwhackers. So George is the member of this team, one of the leaders. That's all for today. Thank you for your attention.
Maybe there are any questions?
I think we have time for some questions.
In the few slides before the demo, how did you discover the name of the header for the certificate number?
As I shown a little bit earlier, here, yes.
Okay, so it's inserted right there. Okay.
Yeah. In this particular case, that was rather simple because the client endpoint of the tunnel was appended these secret headers, so we can easily just look at them.
Right.
But actually, we could have used trace, which returns the headers.
Right.
And we have, not in this penetration test, but in some other penetration tests, it is, we have found, sometimes we have found the debugging interfaces which print out the HTTP headers, or the environment, the whole contents of the environment, which usually contains headers.
And the value of that header, is that inside the certificate, or because it seems like it's only 3 bytes in your demo, but not sure if it was that short or if it was part of the certificate. How did you discover the numbers?
Which value of which header? The certificate number of?
Certificate number.
The certificate number is well, it is not secret. If you're thinking about it, it's in the real in our pen tests, all the values were USR and the short ID. So if we actually do not know the user ID, which we knew because of some other bugs, we could easily just brute force it.
Right, because it's short.
Yes, because it's short and it's a decimal number.
Yes, great.
And
Thanks.
in this specific case, there was another bug in the web application which allowed us to get a listing of all existing users and their user IDs.
So that was even not needed.
Yeah, and the certificate number is related to the user name as well. Right, yeah, okay.
Any other questions? No? All right, well, thank you very much, guys.
Thank you.